the higher the peak is from the original energy level, so the higher it is compared with the original energy level, the slower that step is. So whichever peak is like has the maximum height, okay, and all the other peaks are lower than it, that would be your slowest step, all right? And that will be your, what do we call the slowest step? Starts with an R. Rate determining step, okay? The rate determining step. So basically, if you want the activation energy for the overall reaction, you're going to take the potential energy of the highest peak, and then you'll subtract the potential energy of the reactants. And as it says here, your slowest step, that highest peak, is the rate determining step. Delta H hasn't changed no matter what the mechanism, because remember, delta H is a state function, okay? State functions, it doesn't matter how you go from A to B, the actual change in enthalpy is the same, okay? And it is always the difference between the initial reactants and the final products. You can ignore all the stuff in between. So if you have two different pathways to get from A to B, it doesn't matter, delta H will stay the same. If a collision has enough energy to get over the highest peak, it will have enough energy to get over all the other peaks as well. I would like you to take a look at this diagram and tell me which is the highest peak, peak 1, peak 2, or peak 3. Tell your partner first. Which is the highest peak? It's not a trick question. Which one's highest? 1, 2, or 3? Show me fingers. Yeah, number 1, right? This is the highest. Everything else is below that level, right? So you want Mount Everest, all right? Mount Everest. And it doesn't matter, you know those ones where like the mountain is like underwater, right? And it's actually taller than Mount Everest, but it's underwater. It doesn't matter. Because if you actually look at the difference between here and here, this is probably bigger than that, but it doesn't matter. And that's because in a frictionless universe, yes, in a frictionless universe, if you were to roll a ball over all of those hills, if you had enough energy to get over that first hill, you'd certainly be able to get over the second hill, right? And sometimes people think, oh my gosh, it'll get to the bottom and it'll get stuck. But no, it picks up all the kinetic energy from here to here, right? So it has enough kinetic energy, enough kinetic energy to get back up over this hill, because it gained this much kinetic energy and it only needs this much to get up that last hill. Okay, yes?
Does this like type of, is this still quantum?
Is this what?
Quantum, like really small distance stuff. Like the way atoms move.
Oh, yeah, they don't actually roll over hills or anything like that. They no, but I mean,
these atoms move like they don't lose any energy at all.
We assume they don't lose any energy. Okay, it makes our life easier. All right, yeah. All right, so even though the ball goes very far down into that second valley, it will pick up lots of kinetic energy / velocity in the process of going down that second hill, and that will allow it to get over the third hill, even though the third hill is very high. This is the reaction we had from last day, and if you remember, reaction intermediates do show up in the reaction mechanism. What doesn't show up in the reaction mechanism? The activated complexes, those are in the arrow. So our reaction intermediate, our Huber, appears first in the products. First it is produced, and then later on it is used. And that's how reaction intermediates work. They are first produced, and then they are used up later. All right, so on our graph here, you can see we have 1, 2, 3 steps. So we have 1, 2, 3 peaks. All right, we have each peak has its own activated complex. And those appear at the peaks. And then in the valleys, the reaction intermediates exist in the valleys or troughs. Okay. Yes. They don't exist for very long.
So what if they don't get hit, like they don't come out of the next problem that I used to the next step? Like if you were to
I don't know. Yeah. I mean, if you were to just isolate it by itself, it might break down into the original reactants. Possibly. That would be my best guess if there was not something else. Because the reactants are more stable. Just guessing. Yeah. You guys ask hard questions that I don't know the answers to. And that's okay. You can go and ask your professors at university, and that will be good. Okay? All right, so a reaction intermediate. Without looking at it, could you please define for your partner, someone near you, and if not, do it for yourself, what is a reaction intermediate? Okay, hopefully you remembered it is a substance or a chemical species which is produced in one step and then used up in a later step. The steps do not have to be consecutive. For example, you could produce an intermediate in step 1 and use it up in step 3. It doesn't have to be like the step right afterwards. How do you recognize an intermediate? It appears first in the products, and then later, what did my voice just do there? That was crazy. Later, it appears in the reactants. Okay? Catalyst. There are 4 parts to the definition. And in order, if you are asked to define a catalyst, I would expect you to have all 4. Yes? So you would need to say a substance that speeds up a chemical reaction, speeds up a reaction. How does it do that? It provides an alternate pathway. What is true of that alternate pathway? That alternate pathway or mechanism has a lower activation energy. And you should also mention that a catalyst is not used up in the reaction. So this could easily be a 2-mark question with each of those points being worth 1/2 of a mark each, okay? How to recognize a catalyst in a reaction mechanism? Well, unlike the intermediate that is first produced and then later it is used, the catalyst is first used and then later it is produced. So it appears first in the reactants and then later it appears in the products. So if we want to look at them side by side, our reaction intermediate, first on the right, then on the left, whereas our catalyst is first on the left and then on the right. Reaction intermediates are used up as the reaction proceeds, whereas the catalyst is not used up because it gets reproduced at somewhere later in the reaction, okay? It's not used up, it gets remade. Yes?
Then how would the catalyst really look like? Could it be like aqueous or liquid?
It can actually, there's all sorts of different catalysts, okay? So you can have a solid catalyst. You can have hydrogen ion often acts as a catalyst, okay? You can have, if you're in biology, you can have enzymes, which are catalysts, which are like proteins, and they've got structures that will like grab onto, you know, substrate A and substrate B, and it'll take them and it'll go plonk and bring them together.
So they won't change phases.
Don't worry about the phases with the catalyst. Okay? Okay? Not yet anyway. We might talk about that later, but don't worry about it yet. So let's just take a quick look at an uncatalyzed reaction. We have our uncatalyzed reaction, which is very, very slow. Okay? And then, in this particular case, we have our uncatalyzed reaction here. What I would like you guys to do is I would like you to, using boxes and circles or underlines to keep each one straight, identify the reaction intermediates and any catalysts in this reaction mechanism. Okay, what is one of those things? The H ion. What is H ion? It appears first in the reactants and then in the products. Therefore, it is a catalyst. Do we have any other catalysts? No. Do we have any reaction intermediates?
Yeah.
What do we got?
HCOOH2.
HCOOH2.
CO.
And we also have HCO. Okay, so those are reaction intermediate and reaction intermediate. And if you were to cross all those things out, which you would do when you add up all those three steps, all you would be left with is HCOOH, which is in the overall reaction, CO, which is in the overall reaction, and H2O, which is in the overall reaction. Yes? Who is the rate determining step of this reaction? Step 2. So who would have the highest peak? Step 2. Okay? So here we go. We've got that. That's just, and then we have a little aside. Okay, just a little organic chemistry aside. HCOOH is called methanoic acid. What does the meth stand for? Not just carbon, but how many carbons? 1 carbon. 1 carbon. All right, and then we have the oic acid, which is the ending that we get for a carboxylic acid. So you can have ethanoic acid, propanoic acid, butanoic acid. Do you guys know what the ending of those acids looks like? Their formula? Their formula ends in COOH. Okay, and this COOH is what is known as a functional group. And it's something that replaces hydrogens somewhere on a carbon chain, okay? And every functional group has characteristics that make it what it is. So all carboxylic acids, for example, are acids. Shocking, yes? And if you want to know what that looks like when it's all drawn out, we have C, double bond O, single bond, OH. And then the carbon on the other side is attached to the rest of the molecule. I don't think anyone else says that's what R stands for, but that's how I always remembered that R is just the rest of the molecule. Okay? Some carbon chain or other. And that means that you should, and hopefully you all do, recognize that the formula of an acid either begins with H or it ends in COOH. Now, if we have an organic acid like this oxygen here would have 2 lone pairs on it. There's actually a lot of hydrogens on this molecule. Yes, we got 4 hydrogens on there. And the property of an acid is that when it dissociates, it gives off hydrogen ions. Why is it that it is this hydrogen here that says, oh, little bond, I will let you go. I will let you jump onto the oxygen. Those electrons from the bond jump onto the oxygen, and I will fall off, leaving the oxygen with now 3 lone pairs, as opposed to 2 lone pairs that it started with. So why is it that hydrogen that comes off and not the other 3 hydrogen, the ones attached to the carbon? Yeah. Yeah, so O is very electronegative. What does it mean to be electronegative? Electronegativity is, yes?
Make sure you to fill up the shells or
No. No. Yeah.
In a covalent bond, they're more likely to have the electron. So a higher electronegativity, they would have the electron for higher period.
Yes, exactly. So they have a stronger ability to pull, something with high electronegativity has a stronger ability to pull bonding electrons towards itself. Okay, so it is the ability to pull bonding electrons towards itself. So oxygen is really good at that. So, and the hydrogen is only sort of medium. All right. It's not bad because the ones that are bad are metals. Metals have terrible electronegativity. That's why they become positive ions all the time. But over here we have carbon, and these have similar electronegativities. All right. Next. One of the 4 things in the definition of a catalyst is that it is not used up. And if it is not used up, that means it gets spat out the end of the reaction, and it can then go back and catalyze another one, and then another one, and then another one, and then another one. So only a very small amount of a catalyst is needed to catalyze a large amount of reaction. Okay? So, our analogy, one matchmaker can go around arranging marriages for the entire village. She makes one match and then moves on to the next. Although by interacting with the men and women, she speeds up the marriage process, she does not actually get married to the man or the woman. And therefore, she remains available to arrange more marriages, and the marriage rate in the village continues to be quick. Yes? Okay. Potential energy diagram for a catalyzed reaction. If you want to find the activation energy of a particular step, you measure from the beginning of that step to the peak. So each step has its own activation energy. And for that one, you measure from the start of that peak to the end of that peak. But if you want the overall reaction, you have to start from the original potential energy of the reactants and go up all the way to the highest peak. Okay, and we'll show an example of that on the next page. Or actually, maybe we'll show it here. The following, yeah, we're going to show it down at the bottom of the page. The following is a potential energy diagram of a catalyzed reaction mechanism. How many steps are in this reaction? 3. Which one is the rate determining step? The highest peak. So that would be the second one. And now what I would like you to do is I would like you to label on the diagram the activation energy of the second step, the activation energy of the overall reaction, delta H, the axes, the activated complexes, and the reaction intermediates. Go! So when you're done, you can take a look up here and check your activation energy of the second step, which is in blue. Overall is in red. And delta H is in black. Please take note, with delta H, the arrow does not look like this. It should start at the level of the reactants and it should finish at the level of the products. Okay? And where do the activated complexes go? On the peaks. There we are. And where do our reaction intermediates go? In the troughs, in the valleys. Okay, so there they are in between. what should we label the x-axis of this diagram? Reaction proceeds will work. Any other way we could do it? They tend to stay away from time, and I'm not quite sure why. I think it's because time implies that, you know, you should have like 1 second, 2 second, 3 second, whereas we're really ballparking where the actual times are. Do you know what I mean? So it's not really time, because this could be 10 seconds and this could be 1 minute, and you know what I mean? Yeah. So we'll say the reaction proceeds, and then that is, or progress of reaction. And there's one last way we could do it.
It's like reaction form.
Reaction coordinate, which, like I said, I can barely remember. So I would not expect you to be able to come up with that, but just don't get like weirded out by it if you see it. Okay, that's what it means. Coordinate. All righty. What do we label our x-axis? Potential energy. And what is the unit? Kilojoules per mole. Excellent. Okay. There's the answer. Blah, 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 blah. So if we have a potential energy diagram of a catalyzed versus an uncatalyzed reaction, put a star beside this. If you are given the catalyzed mechanism, you are going to include the correct number of peaks. How many is the correct number of peaks? It's the number of steps. So if I give you a 3-step mechanism, you're going to have 3 peaks. If I give you a 7-step mechanism, you're going to have 7 peaks. Probably I wouldn't do that because that's too many, but that's okay. Too hard to draw. If we were to look at this one here, you can see that the activation energy for the uncatalyzed reaction goes all the way to the tippy top there. The activation energy for the overall catalyzed reaction is from the reactants up to the highest of those 3 peaks. Yes? Yep. Well, I mean, technically there could be another mechanism there, but we don't know what it is. Okay? And if we do not know what the mechanism is, then just represent it with 1 peak. Okay? All right. And delta H, of course, remains the same. Now, what if you are not given the catalyzed mechanism? Are you expected to guess how many peaks there are? No. All right. You're just expected to say, okay, I don't have a mechanism, so all I know is that the activation peak of the catalyzed reaction is going to be lower than the activation peak of the uncatalyzed reaction. I'll just put 1 peak there. So given the reaction, use the right number of peaks. Not given the mechanism, just use 1 peak. Okay, there's some questions in Hebden, which are there. And we are going to move along to kinetic energy diagrams, which are on page 105. Yeah.
Are all multiple peaks diagrams with catalyzed?
No, you can have mechanisms that are not catalyzed. So like that Huber-Hober one, there was no catalyst in that one. Okay? Yeah. So consider a beaker of water sitting on a counter. The individual water molecules in the beaker are in constant motion. But this is not the important part. The water molecules are not all moving at exactly the same speed because they do not all have the same amount of kinetic energy. They have an average kinetic energy that is all the same, but they're not all moving at the same speed. Some are very energetic, high kinetic energy, and they move very fast. That would be these blue ones over here. These ones over here are very, very fast. So some of the molecules are very fast. Not a large proportion of them, only some of them. Some molecules are very slow. Those would be the ones on the low end of the kinetic energy scale. So kinetic energy is low over at the left and it is high over at the right. Now, what's happening on the y-axis? The y-axis represents the number of particles. Okay, so the area under the curve represents the total number of particles. Okay, area under the curve represents the total number of particles. Does this graph look familiar? It should. If you didn't do the gases stuff, go back and watch those gases lectures. You can go back to, let's see, the Chem 11 enriched team, and let's see, lesson videos. And you can be like, okay, going back to, oh, look at all these. Oh, there's gases starting at January the 23rd. There you go. Okay, so there were lectures. And if you've lost the book, it is posted in Teams. Also, if we go to our general channel files, moles, bonding, gases, unit 13. Okay, so there you go. At any rate, this thing is called a Maxwell-Boltzmann distribution. And you will notice that it looks a lot like a bell curve, but not quite. It is skewed to the right. In other words, the right trails out a lot further. And this right here is an asymptote. Is there a P in that? Or is it just asymptote? There's a P? Okay, good. Thank you. I thought so, and then I had a brain. AP Chem, you'll call it a Maxwell-Boltzmann distribution. In regular Chem, you'll hear it referred to as a kinetic energy curve or a kinetic energy diagram. And that's because what's on the x-axis? Kinetic energy. Now, that's different because kinetic energy is on the x-axis. In our potential energy diagrams, potential energy is on the y-axis. So, but we put activation energy, we can label it on both types of curves. And so that sometimes people get messed up because they forget where the energy is. So just remember, always look at your axes, okay? Yeah, we talked about that already. The area under the curve represents the total number of molecules. The peak of the curve, right here, that is our most probable number of particles have that amount of kinetic energy, okay? So if you were to sample any molecule, all of the different speeds, you would most often run across that particular kinetic energy right there. All right. Recall, activation energy is the minimum energy with which particles must collide in order to form an activated complex. So let's say that right here we have this activation energy, and let's just say that this is 10 kilojoules, okay? All the molecules that are slower than that have less kinetic energy than 10 kilojoules, will not react, okay? All of the molecules in the green section have either 10 kilojoules of energy or more, which means they have enough to achieve the activated complex. Now, if you had to guess the fraction of molecules that would have sufficient energy to react, that would have 10 kilojoules of energy or more, just by looking at that thing and saying, what fraction is that of the total area under the curve? What do you think? You can really ballpark it. Yeah? You don't have to do a great job of it. What I would do is I would be like, okay, I've got an area that's about that big. And then what if I did the same thing over here and the same thing over here? And then I was like, okay, I need something a little bit bigger, and then a little bit smaller, and then 1, 2, 3, 4, I don't know, 5, 6, 7, 8, 9, 10, 11, somewhere between 10 and 11, maybe 1/10 or 1/11, something like that. I think in my last class I came up with 1/12, but you're not going to get it that close. But at any rate, it's somewhere in the 10% range, yeah? About, let's just call it 1/11. Doesn't matter. You're not going to have to do that estimation anytime, okay? But what you need to realize that this is a small percent. Now, what if we had a different reaction that had a smaller activation energy? Smaller activation energy. Say this is, I don't know, 3 kilojoules, whatever. So all the molecules that have 3 kilojoules or more will have enough energy to get over that peak. Approximately what fraction is this of all the molecules? It's the majority, okay? We're looking at, I don't know, I think in the other class I called it 9/10. Let's call it 9/10 just because I don't want to get too excited about it. But we've gone from a low percentage to a high percentage. And that's why we talk about the percentage of collisions which are effective or the fraction of collisions which are effective, is because we are looking at the fraction or percentage of collisions in here that are effective. And I think, are we, what time are we done today? Today is till 1:40, so we got 5 minutes. Okay. So don't forget, temperature is a measure of the average kinetic energy. And as average kinetic energy increases, what is going to happen to our peak of our graph as average kinetic energy increases? If you did gases, maybe you remember. What's going to happen to our most frequent number, our mode? It's going to move to the right because the most frequent temperature will move to the right. There are going to be fewer slow molecules and there's going to be more fast molecules, right? So our average kinetic energy increases, therefore the peak moves to the right because the peak is, it's one of the averages, okay? There's several different averages, but that's one of them. The fastest of the molecules, so the end of that curve is going to be further to the right than before. So the fastest molecules are further to the right. So the tail is going to stretch out further to the right. Have we changed the number of molecules, though? No. So that means the area under the curve must stay the same. And if the area under the curve stays the same, then the whole thing needs to get flatter. Yes? Because if you've got, you know, something like this has the same area as something like this, right? Same area. So if it gets shorter, it has to get flatter. Do we need to go over why that is, or can you just remember that? We're good? Okay. The other thing to notice is that these never actually touch 0. Okay, so you can kind of be like, okay, it's getting close to 0, and then not quite. Okay, so you're not going to be like, oh, it goes down to here, or whatever. In fact, I would tend to have it trickle out, and I'd be like, close enough. Yeah? Yeah. On the what? On the slow end, because you can't have anything lower than, because if you're at 0 temperature, there's 0 molecules that have a. Why doesn't it all move over? Because there's always going to be molecules that are close to 0 speed. So you'll just have fewer of them. Does it make sense that like if you had a whole bunch of molecules that are going really fast, but they bashed into one another with exactly the same amount of energy, then they might just like cancel each other's motion out and they might just stop for a second. Do you know what I mean? So on average, yes, all the molecules are getting faster, but there are going to be some that are slower just because of the way they're colliding and that kind of thing. Does that make sense? Yeah. Okay, so when temperature is increased, you need to remember 3 things, and that is that the peak moves right, the peak gets lower, and the curve gets wider, and vice versa when temperature is lowered. And we are out of time for today. So your homework is these things, but also to work on the review so you can come in with questions for next week. Now, if you're like, my God, that's way too much, I can't do all of that and all of that, then just do some of these and some of that. Yes? Measure out your time as best suits you. Yes? I know it looks like a ton. It's not really a ton. Okay, it is. And I'm going to go grab my water before my grade 9s get here. So I will be back.
We're from Mr. I need to get my PR or. Domestic or. Like one. Oh, you're planning to.
Yeah, we're doing a quiz and then watching.
I don't think that works for you, but I can offer it's like. Okay, you have 2 minutes here, okay? You better. You better see by the way. Because I won't write. You never want to write. Right, yeah, I'll get it right. No, I want to write. You just like. Oh, okay, so you're, free.
Well, that's-
That means I would never, ever want to ride before. I think we can just she's a bad driver, we should change it. Yeah, okay, stereotypes about the, even if that's not. Yeah, in fact, that's not. I still have some. You know, I just. It's not bad. I'm not like, every school, you throw everything out. You just throw everything out. Yeah, how did we get from? Sure. I think you're, I come on. Sure, yeah. Hello. Okay. That's a while, so just a minute. Yeah. Did you pass? No.
Cora, Stellenberg to the office.
I was just gonna say, right now, the. Well, I mean, honestly, my brain is. No, I didn't.
Oh, goodness.
Elevator path. Please remember to hand it in before you leave today.
Hello,
Hi.
39 to 41. Yes, indeed.
39.
Very good. These look beautiful. Yes, and you've got all the things you need. Wonderful. Hello. Great. That looks great. Those look good. And don't forget that you want to put whatever you're measuring. Yeah, so all of those you gotta remember those, okay? All right. Malia. Yeah.
I do not want to sit down.
There she is. Hi. Hi. Okay, that looks good. Yes, yes, yes. Very nice. Thank you so much.
Yeah.
Hello. Right. Now, you know what you've forgotten? What you're measuring. Okay? But other than that, it looks good.
This is a normal.
Hello. Those look great. Hello. You know what you've forgotten on most of them? What you're measuring. Uh-huh.
Put that in.
Uh-huh. Okay. Yeah, that looks good though. Other than that.
I'll go put it on.
Yeah. Who's down here? Here she is. Hi, Paula. Very nice. And don't forget, you need to put what you're measuring. Oh, so you're going to put what you're measuring, what you're measuring. Okay. Other than that, though, it looks good. Okay.
I didn't have time to finish the done.
Okay. And you want your unit? And you want what you're measuring. Okay. There you go. There we go. Hello. Excellent. Don't forget what you're measuring.
Oh,
Yeah.
I knew something was missing.
Right? I know. It's like fun. Okay, but other than that, it looks good. Thank you. Oh, thank you. Yeah. Hello. All right, this is beautiful, and you've remembered to put what you're measuring, which lots of people didn't, so very good. You forgot one unit, but other than that, it looks great. I forget where it was. It was on the next page at the bottom. There. Oh, yeah. Sophia, there we go. Hello. All right, you know what you forgot? Which, what mostly everybody, what you're measuring. Okay, so for all of those, you'll want to go and do that. Yeah, you did it here, so that's great. Perfect. Okay, so remember that all the time and you're good to go. Hello.
Yeah.
All right. You, along with everybody else, has forgotten to write what you're measuring. Right? So you would say length equals, yeah? Yeah. But other than that, those are looking good. Perfect. Okay, so just write what you're measuring and you're good to go. Okay, thank you, Marco. Mateo. Oh my God, what's wrong with me? Ah. All right, you and everybody else has forgotten to write what you are measuring. Right? So you'd be like length equals. Yeah? But other than that, it looks good. Okay? Yeah. All right, that was from there we go. Hello. Excellent. You and everybody else has forgotten to write what you're measuring. Okay, so length equals or whatever, but other than that, it looks good. Thank you. Valerie. There we are. Hello. So nice. Okay, very nice. Thank you very much. And you remembered to write what you were measuring, which hardly anybody did, so good for you. Hi, Maya.
I think.
Right.
Which one was it?
It was this one, yeah, and this one here, and so exciting. You remembered to write what you were measuring. Yes, just use an equal sign rather
Okay,
than a
yeah.
colon, but other than that is perfect.
Thank
Okay,
you.
yeah. Maya.
I can.
Hello, Hudson.
20
Uh,
or 39.
Yeah. Okay, perfect. And you and every other person in this class, not just you, forgot to write down what you're measuring. So this, for example, would be length. Oh, okay. So don't forget to do that. And but other than that, these look good. Okay. Yeah. Thank you. All right. Very nice. Now you have forgotten to write what you are measuring. Okay. Okay, so that is it. Thank you very much. There we are. Hello. Excellent. You and every other person in this class forgot to write what you're measuring. So for example, this one here would be the length. So you would write length. Okay? And other than that, it looks good. Kira. Hello. Okay. You and every other person in this class forgot to write what you're measuring. Okay? All right. Aria.
I also have a question. Do you remember what it is?
Yes, I've taught a couple of Aryans. But yes. Your brother. Hang on.
Make sure you're measuring.
Yes.
What you're measuring.
Yes. Yes. I've taught several Aryans, so I just needed to remind myself which one.
Yeah.
I
did not.
Where is
mine?
Cool. Cool. Say hi from me too. All right, friends. Let's see. Kira, do you have your homework? And Ryan? You're doing it? Okay. This is good. And yeah, those are better. Yeah. Nice. Thank you. That was always fun. Hello. All right. And you are now putting in your lengths and things. That's good. Okay. Yeah. Very nice. All right. And where are you? You are Zoe Watt. There we go. Thank you.
What the?
Hello. Beautiful. Beautiful. And you got those. Very nice. Thank you, Vivian. Hello, Kira. Very nice. Thank you very much. Austin. Okay. Logan, do you have your homework? Okay, so either show it to me on Monday or come in Tuesday during flex and do it for me. Okay? Yeah.
Why are you cutting my
Those are hilarious. And Abby is away today. Okay. Abby's away. Yeah. Okay. Science 9. There we go. All right. Okay, we're just going to take a quick look at page 39. Because next Tuesday, there's going to be a quiz on making measurements. Tuesday, there's going to be a quiz on making measurements. All right, so I think everybody got it correct that this is a ruler. Yes? Okay. So this is a ruler. And almost everybody in the class forgot to write down that we were measuring the length. Okay? So you would want to have length or just L. L would be fine. And then equals. And then we're going to take a look, zoom in up here. This one in the middle, this is 9.5. So we are somewhere in between 9.6 and 9.7. So this should be 9.6 something. right? And you can pick what you want it to be. I would say maybe 9.65. But if you don't have 2 decimal places, that would be 1 mark lost out of 4, okay? And if you don't understand why you need 2 decimal places, let's remember once again, you look at what each little line is worth. How much is one little line worth? It's worth 0.1. So that means you need 1 extra decimal place. Okay, so whichever one you have, you need 1 extra decimal place. And I think most of you are really good at having your units there. Okay, so that's centimeters. So almost everyone forgot this one. So on Tuesday, what are you not going to forget? What you're measuring. Okay? And how are you going to know how many decimal places to go to? Tell your partner. How are you going to know how many decimal places to go to? You're going to know what's the smallest line worth? And then you go 1 more decimal than that. Okay? So what's the smallest line? Go 1 more decimal than that. But you are guaranteed 2 marks if you got 9.6. And even if you didn't have the 5, you'd get a mark for being like reading it correctly and not putting 4.7, right? Because 4.7 would obviously be wrong. And then you get 1 mark for saying centimeters. So you definitely get 2 marks out of that if you can remember your units as well. And then don't forget what you're measuring. And this is the hardest one usually. What is the smallest line? Go 1 more decimal place. All right. Now we're going to go back to, this is a quadruple beam balance, okay? Quadruple beam. And that's because today we are going to start using the quadruple beam balances to do a little activity, okay? So we are going to take a look at this example of a quadruple beam balance. And you are going to tell your neighbor what quantity does a quadruple beam balance measure? What quantity does it measure? And if you want a clue, there's a little clue there. That's the unit. Grams is the unit. What is the quantity that it measures? That's another unit. Kilograms is another unit. Yeah, mass. Okay, mass. All right, so it is mass. So when you are reading this, you want to say mass equals. In fact, I'm going to cross that out. I'm going to write mass equals. And then this works just like a triple beam balance, but there's more pointers to read. So in this case, what's our first number going to be? Yeah, 100. So we have a 100. So I'm going to put a 1 for the 100. And the next one is 80. So I'm going to put 1, 8. And then the next one is a 2. Are we unsure of any of those? No, we know those for sure. This next one is where it gets tricky, okay? So if you can get this, you're like at the top of your game. If you don't get this ever in grade 9, it's okay. right? Like you may be like, okay, grade 9, I don't necessarily get this, but you can try. Yeah. Point
300.
It is indeed 0.300. Now let's take a look up close. Why is it not just 0.3? Are we unsure about that 0.3? No. What is each little line worth? Each little line is worth is 0.01. So you need to go one more place. So that's going to be the 0.0, and then you'll have there. Okay, so it's going to go there. So you need to now have 3 decimal places, not just 2 decimal places. But remember, you're in grade 9. This one is really tricky. If you don't get it in grade 9, that's not the end of the world. Okay? So this would be 182.300. Let's make that 0 look like a 0. Do you like my answer? What's missing? Units. Grams. If I said, please show me the uncertain digit, which is the uncertain digit? That's our last one. That's our uncertain digit, or estimated. How many sig figs are in that number? There are 6. 1, 2, 3, 4, 5, 6. Remember zeros? Do you remember the little trick I taught you to remember? No. Yes. Maybe. NYM, NIM. So if they're on the left, don't count them. So if I had some zeros here, we would not count them. If they're in the middle, we would. Yes. At the end, it's maybe. And we ask ourselves, is there a decimal? And if there is a decimal, then the answer is yes. So if we say decimal, yes. Significant, yes. Decimal, no. Significant, no. Okay, so this has 6 sig figs. All right, and that gives you a general idea of how to do those ones. And now you get to do the activity with the actual quadruple beam balances. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so we need to be in groups of 2 or 3. If people could not work on their own, that would be wonderful, because otherwise we will run out of balances. Okay, so maybe 1, 2, 3, you guys, 3 guys at the back could work together. Would that be okay? Yeah. Okay, awesome. All right, and the rest of you have someone you're sitting with or 2 people you're sitting with. So you're going to grab a balance, and I'm going to hand out 2 things. I'm going to hand out the activity, and I'm going to hand out a picture of the balance that's labeled that will help you answer the first few questions. Okay? All right, balance.
Oh, that was bad.
Would someone like to hand something out? Yay, Cody, excellent. One of these. Okay.
Okay, that's not work. That's one of them. I would get that. I would take the wires in my mouth.
So ladies and gentlemen, each of you. Each and every person is going to fill this out. So it's not one per person. Okay, I want you practicing making the measurements. So when it comes to Tuesday's quiz, you do a really good job with it. Okay? Read the activity. If you're like, I'm not getting it, it's because you haven't read it. Hello?
I got like a weird, I would like to say.
Oh, okay, yeah. If you do not get one of these to help you with page 2, then let me know and I can get you one. I've messed things up, so you have to do it. We're all strong. How many of these?
Oh.
You didn't get paper? Oh no. I'm so sorry. There you go.
Oh my god. Oh my god, why didn't you get it? Of course it gets used though.
Okay.
No, like, oh. Yeah, right. Yeah. Right. Oh, yes. Oh, oh, we got them. Oh, sorry.
An activity with balances.
Okay, so you look now. Oh my God. Okay.
Or what?
Let's go. Yeah, we're just talking about here. And you're Okay. Zero? Oh my God. Okay, okay, so which way do you need to make this? You are so lucky. You are. Sometimes they don't work well. It might be good.
If anyone has tab number 20, let me know. It is close enough.
Okay, there we go.
Oh, that's nice. All right. It's pretty good. Oh, right.
It's just a little bit high. How would you make it?
I think it's a question about.
So excited to get you ready.
So that's right.
But you were ready just now because you were like,
I'm on that beautiful.
Get on it. Squishiness. There you go. There you go. Okay. Okay. I am going
You're all kind of.
Right. Oh, hello. All right. Good. Down. Clockwise.
No, I didn't.
I know, I have to go until it is.
So we see.
Maybe it's just like. All right. Oh, yeah.
Okay. Although actually, that's right. But that's hard. We're gonna say. Right. You're almost correct. Yeah. You are correct. Yeah. All right, let's do it. It's good. Okay. Ooh, electronic balance is neat. What do you say? Hello. Is he doing government? I know. I'm looking for it. What is Folks, when you get to the part with the electronic balances, they are on the start, on the top shelf, on the middle shelf, on the bottom shelf, so you might have to look around. And there's not enough for everyone, so when you are done with it, either put it back or let everybody know that where the balance is set up. You can set it up on long outside counter or something like that.
Yeah. Yes. You gotta get ready. Add that on the table. Yeah, they're on that word. You. Well, why you going that way? Almost good. Oh, zero, right? What finger, what finger, what kind of mouse are you using? Oh, yeah. There are one Oh, using 5A.
Oh. Alright.
Okay, so that.
Oh, wait, I've got.
All right, what do we got here? Most beautiful. I'm so
Is there a well?
Oh, this
As
is
a
the
member.
so the smallest line is 0.1. So then you're going to read it to 1.3. So does that make sense? Yeah, it's like workplace. I didn't sign this, I'm so sorry. You're like, I'm just gonna lie. No. See, this one says me.
Just water. Water keeps house.
Oh, so that hurts? Like mid back or? Oh, that will do it.
I'm sure it's.
Second thing.
Wait,
Yeah, it was. Yeah, it was.
That's what it has to be.
Really? Okay.
I didn't know.
My yellow.
Sweet.
Oh, no,
Pardon me? Yes, just sign out and grab the hall pass.
Wait. You got the.
You got it? Okay.
Oh, wait, no. We don't need
I'll just in a second, these guys let their hand up first. Hello.
Yeah, we can use that.
Hello. All right. Is that now? Of the second. No, you gotta say math. Good.
Now it's secret. Yeah, this is worth it.
Go fit your.
We're waiting for on balance.
Guys, when are we gonna be done with the baby?
Hey, is anyone done with their electronic balance? Are you guys done? You don't like when it's sharing. So, yeah, I think it's better. Using? Or we'll slide in between them. Either way, you're good. Okay. Yes. So you're just gonna wait. Okay. I know.
What is it?
Probably my great calls you're ready to play this. Oh, yeah.
I mean, it's kind of.
Why would you have said? Oh.
Oh, you can knock it off.
Folks, when you're done with page 5, you're done with the electronic balance, and you can return it so someone else can use it. Okay? I think they're done with theirs, you guys can grab that. Here, not, just heavy. Yes, you guys forget. Hello. Oh, no. No, left means all to the left of mouth. In between them.
Why doesn't they change?
Mr. Love, did you get what you needed?
Yeah, she lines up.
Yeah.
So
One on one. Oh, it just said one, 101. Wait. Wait, when you cross off PP. Very nice. Very good. Great, it's really fun. It really
Are you not? Well,
then you add one to this digital.
Just open your sense. Very Yeah. No, we need it. No, it's not. I think it'll do it.
Okay, so is the mass of the water 90.150 liters? Is that the mass of the water? So we use only phase out. So first of all, with the mass.
Wait,
Okay.
some of the electronic.
Okay.
I'm just curious. Come on over here for a second.
6, 7.
At how many there are,
All of you. Okay.
yeah,
Oh, yeah, okay. So you see how I got a decimal and then 2 digits? And do you see how they went low on it like that last one around? That is our conservative. So when it is digital, don't have it. Does that make sense?
oh, R, oh, yeah, R. I mean, at any rate, it's digital. Yeah.
You can have someone else.
Yeah, oh my God. Yeah, that's crazy. We're still.
Did you guys pick that up?
I need to finish this. Believe me. What?
No, we have the Monday as well. Hello. So folks, as long as you get done, as long as you get done part 11, you can do the rest of the homework. Okay? So we have 15 minutes left. So you should finish it and then finish anything extra that needs doing for homework. But you might even be able to finish it today and not leave it. Okay? Yeah, you don't have to do this. Your choice. Okay? Yeah. Start just going.
Oh, this is around.
Ah, okay, so we are looking at. And tendency is a
No, seriously.
No, actually,
Yes.
Yeah.
Like substitute.
This number.
Leaving more.
So, wait, we have to go. Wait, are you? That's not.
No, this is water.
Yeah. So.
This intercom is about, yeah.
Oh, yeah, no, yeah, two.
Hello. Yes.
Okay, yeah.
Andrew,
I really like that.
oh, yeah. That's. Oh, yeah, that's. Oh, yeah.
Anything that's on the top.
Your mom.
Yeah. Yeah.
Yeah.
So that's good.
Oh, actually, this is gonna be the other way around because otherwise you're gonna put.
Yeah. You just swap. I just rather.
You can just write arrows, yeah, I'm good with that. Folks, if you need to borrow a calculator, you can do so. You just need to give me some collateral, something in trade. And then when I get the calculator back, you get whatever it is back. You all done? Fantastic. Perfect.
You don't pay.
Oh, circle.